I'm Charlie Reis from the Chrome site isolation team. We're honored to be recognized for our work on improving browser security. Here, I'll give an overview of site isolation and its impact on keeping users of the web safe. Now, when you step back and think about it, the web is built on a very ambitious goal, that it's safe to run code from any website on your local machine. And much of our lives now depend on this goal, given how much we do online today. But this is a very difficult goal in practice. Behind that premise, each site is a full-blown program from a possible adversary. We compile that program down to native code, and we run it inside a complex and evolving system, which is written mostly in unsafe C++ code. It is not easy to secure this platform, and there will inevitably be bugs that are exploitable and that attackers have access to from their code. Clearly, we need to find and fix those bugs, but it's just as important to limit the damage that they can cause, since these bugs will be found. For this, the browser's architecture matters for how we can lessen the severity of bugs when they're found in the wild. The most obvious example of this is adding a sandbox. And we long ago moved from monolithic web browsers, which ran everything in one process, to multi-process browsers with sandboxed renderer processes. This keeps a lot of the risk inside the sandbox, which is low privilege, and makes it harder for an attacker to take over the client, even if they know of a bug inside the rendering engine. Now, moving to a multi-process browser architecture wasn't a trivial change, but we could basically port existing rendering engines to a new platform, which would be running inside the sandbox, and then run multiple copies of those in different tabs. But this still wasn't a great match for the web security model. We still had to rely on code within the legacy rendering engine to enforce the same origin policy itself, the security model of the web. And because that ran inside the sandbox, we couldn't get the guarantees we wanted. And part of the reason for this is that even new browser architectures at the time, like Chrome, still inherited a decade-old rendering engine. In our case, WebKit dated back to KHTML in 1998, because you just couldn't easily build a new rendering engine from scratch without breaking compatibility with existing web pages. And so this meant that we can't adequately protect users' accounts if things like cross-site iframes or pop-ups live in the same process with an attacker's page. Now, we'd wanted dedicated renderer processes for each site for a long time. But in this case, it's not as easy as just running another copy of a WebKit rendering engine. So site isolation was our effort to solve this. And that meant re-architecting the browser to be more like an operating system, which is the role that it's playing today. We needed to be able to run separate programs with different security principles in separate processes. And that could give us strong boundaries between these programs. The biggest challenge in this work by far was supporting what we call out-of-process iframes. And that required overhauling the rendering engine, which thought it was in charge of rendering an entire page. But on the web, things like cross-site iframes, such as embedded videos or ads or maps on other pages, needed to be moved to a different process. And here, we couldn't even begin this work until we forked the WebKit rendering engine into Blink in 2013. And that gave us the freedom to make more extensive changes to how the rendering engine worked. And this work did affect most of how a browser works. In any frame, you can navigate a document from one origin to another, and that may require creating a new process. When you paint a web page, we now need to composite textures that are produced by different processes and not leak those to a process for a different site. We need to know where to send input events. We need to support certain types of script interactions, like post message, that are allowed across sites, now across processes. And of course, none of this was made easier by the need to support backwards compatibility with existing sites that might have depended on particular browser behaviors. And that was just the architecture work. Then there's a huge list of features in a browser that also assume all frames of a page live in the same process. You can pick any of these and think about how a screen reader for accessibility reads out the content of all the frames in a page, or printing something to a PDF format uses a different layout engine that then produces a single artifact, or finding text within a page. These all become distributed actions that need to deal with content across multiple renderer processes. This took over 5 years of working with various people within the Chrome team to update all of these features. And over 400,000 lines of code changed. This was a massive effort. But we were able to pull this off, and we were able to add support for out-of-process iframes to Chrome. As a result, we ended up with the ability to have dedicated renderer processes. That means we can now track security principles at a process level and say which site has documents in that process. The browser process can enforce access control on these processes to say, do they have access to cookies or other storage? Do they have access to permissions such as camera and microphone? And it can help avoid confused deputy problems where a renderer process claims to have access to something that it shouldn't. But even that was still not quite enough to meet our security goals for a web browser. You also have to think about what data is allowed into a renderer process, because unfortunately, you can't just block all cross-site network requests. Web pages depend on having sub-resources that can come from other sites. And JavaScript is an important example here, where you can ask for JavaScript from any website and then run it as part of your document's own security principle. So we have to let through JavaScript files, as well as images and other types of media and sub-resources into a renderer process, no matter where they come from, while keeping out sensitive cross-site data like HTML and JSON. And of course, sensitive data isn't cleanly labeled on the web, which makes it challenging to build a filtering layer while preserving compatibility with data that might be incorrectly labeled. It's also very important to preserve performance and not to overwhelm the client with process overhead, as site isolation does require more processes. So we worked hard on optimizations, such as same-site process sharing, to keep memory and latency overhead low. We were able to keep that memory overhead to just 9 to 13% in practice, which proved practical to deploy given the security benefits we were getting from the architecture. Now, the first major impact from this work was meaningfully making exploits harder, now that a renderer bug wasn't sufficient to attack other websites. This basically eliminated an entire class of universal cross-site scripting bugs, because an attacker couldn't just find a bug in the same origin policy code to then attack other documents from other sites in the same process, because those documents lived in another process. This meant that attackers must now find a second bug, either a privilege escalation bug to the browser process or kernel exploit, in order to attack the user's cross-site accounts, which is much harder. This means we're now getting the benefits of not just protecting the user's machine with the sandbox, but also protecting the user's web accounts with the sandbox. The second major impact from site isolation was unforeseen, but intertwined with our launch. Spectre and other transient execution attacks really upended a lot of assumptions across the industry by leaking sensitive data via the CPU's predictive behavior and its cache. It turned out that any data within a process became vulnerable to this type of side channel attack. And there were many types of transient execution attacks based on different properties of the hardware. Unfortunately, it turned out to even be possible to exploit this from JavaScript code. And that means with no bugs present in the browser. This is a huge challenge for web browsers, where cross-site data or other privileged data was commonly found within a renderer process. Ultimately, we now have to assume the data in a renderer process is vulnerable to Spectre attacks. Turns out that other mitigations like course timers or compiler changes weren't viable in preventing these attacks from happening. And there's a paper from the VA team called Spectre is Here to Stay that plays out arguments for this. Site isolation instead provides a defense by putting data we're stealing out of reach, outside the process. So this is now part of an important story where you need to align your system's security model with boundaries that the OS and hardware can help you enforce. And that's particularly true in a web browser. This also means having effective process boundaries themselves, such that OSs have a responsibility to help defend against cross-process attacks like Riddle and Fallout. So we're very happy that this work has had impact on the industry, being deployed across many browsers to protect users. We shipped site isolation in Chrome for all websites on desktop platforms like Windows, Mac, Linux, and Chrome OS in 2018. And we've recently extended that to isolate all extensions from each other as well. We've also shipped a form of site isolation on Android for a subset of sites since 2019, and have recently increased the number of sites that are protected. On mobile devices, resource usage is more constrained, so we have to be careful about isolating the sites that matter most, such as sites that users log into. All Chromium browsers now benefit from site isolation. We're very excited that Firefox is working on their own implementation in Project Fission. As a result, site isolation is now an important part of secure browser architecture. And it's important to continue to improve it and close the gaps, things like the difference between origins and site-level protection. We have a 2019 paper if you'd like to learn more, and it's great to see that there are researchers already studying how to improve it. We're honored to be recognized today for this work, and that it's played a large role in protecting users on the web. Thank you.